Well, the data is in on the loan application processing study. I'm going to conduct some statistical calculations on the test to determine repeatability and reproducibility variation. But I want you to know how the data should be recorded to allow that analysis. In this case, each part is a single loan application form. We had the forms available to us from the past year, so we used 10 forms randomly selected from that historical data and numbered them from 1 to 10. For our gauge R&R, we did the 3 recommended trials per part, per operator, and that trial number appears in the first column. We also used the 3 recommended operators, assigning them numbers 1 through 3. The operator number appears in this second column. In the last column, the actual application processing time that the operators recorded appears in hours. So now that the data is ready, I'm going to run the test. Click Next, and I'll walk you through an evaluation of the results. Here are the results of the gauge R&R. The first number to check is the total gauge R&R. The rule of thumb that you should use when evaluating the total is that less than 2% is desirable and up to 8% is marginally acceptable. So the bottom line is that our measurement system is adequate because it is only responsible for a fraction of the variation. However, before we leave this subject, I want to explain the other numbers you see. Under total gauge R&R, you see the separations by repeatability and reproducibility. In this case, the repeatability, or equipment variation, is only 0.001, and the reproducibility, or variation due to operator, is also only 0.001. The remainder of the total variation in the data is the part-to-part. That is the actual process variation, or in this case, the actual difference in the time it took to process an application. So this test completes the measurement system analysis, and with these results, we can feel confident that the measurement system is adequate to capture the capability of the actual process. Before you leave Measure, we have one more task, that is to make sure the actual application processing time data is in the proper form for analysis, much like we just did with the gauge R&R test data. Click Next for our final task in the Measure phase is to give you the necessary skills to develop and improve business processes, not to turn you into a statistician. However, statistical analysis of the process is an important part of identifying and validating the improvements we make, so you need to be familiar with some statistical measures. To make this easier, GE has purchased a tool called Minitab that performs the calculations for you. Minitab is a strategic software package that we will use to understand and analyze our data. It is part of the core load of GE. The gauge R&R analysis we just looked at is an example of what Minitab can do. Minitab was used to run a test on the data and generate those results. You can find more information about Minitab in the Resources section of this course. Your first job is to put the data in correctly so Minitab can do its work. This is much like what we just did with the measurement analysis data. Before you leave Measure, we are going to put the loan application processing data for the past year into Minitab. Then, in the Analyze phase, you'll look at some of the reports. The worksheet area of Minitab is where you enter the data. It functions much like an Excel spreadsheet. Numbers can be entered in columns or rows. However, the default setup of Minitab is columns, so we'll use that format. Column titles are entered here, and then the data below. Click Next to look at the commercial loan sales data. GE measured the application processing times over the course of a year and recorded them in a database grouped by month. There are approximately 110 data points per subgroup, but the subgroup size does vary depending upon the month. Here is the data. In this case, we have just 2 data columns. The first column indicates the subgroup. In this case, that means the month in which the data falls. And the second column contains the measurements themselves. So the measurement of 42.6 hours, indicated by the red arrow, was the first piece of data recorded during the second month. If you wish to experiment with this data in Minitab, the project file can be found in the course Resources, accessed from the left-hand menu. Click Next to summarize the results the purpose of a data collection plan and determine the data to be used for the GE commercial loan sales case. You've learned several terms related to measurement system analysis. and can recognize possible sources of variation in a measurement system. You've learned how the measurement system analysis checklist can guide your validation of a data source. And finally, you've become familiar with the role of Minitab in a Greenbelt project and have prepared the loan application data for analysis in Step 4. Click Next to review our Step 3 results for commercial loan sales. In preparation for Analyze, let's summarize where we are in the commercial loan sales project by taking a more visual look at the data. A good starting point for data analysis is generating this histogram in Minitab. It shows you the frequency of occurrences for a given measurement, in this case, application processing times. Based on the results of the gauge R&R, we know this data was collected with a valid measurement system. The graph shows that several measurements are over the upper spec limit of 72 hours, and a few are under the 24-hour lower spec limit. And most of the measurements are over the 48-hour target performance. So it appears that our current loan application process is not doing too well. In Analyze, you'll verify that problem and look for some reasons why it is occurring. Click Next to finish up our data collection discussion. Well, we did it. We're at the end of Step 3, and that means the end of Measure. Great job! Before you get into Analyze, I'm going to send you back to Siggy. He wants to give you his brief review of Measure and see how you're doing.
The beginning of Analyze.
Click Next to go to the
You
review.
can't set a measurable goal without a clear understanding of where you are. Here in Step 4, we'll determine that starting point. When you click Next, we'll look at the learning objectives for this step. In Step 4, we need to accomplish a number of things. They all involve determining the capability of our process. Let's look at the learning objectives for this step. By the time you finish this lesson, you will be able to explain the key statistical measures used to determine variation in a process, define short-term and long-term process capability, and how to calculate various factors such as Z-bench, Z-long-term, Z-short-term, and DPMO. Evaluate the results of the process capability report. Explain and evaluate the results of the product capability report for discrete data and describe the different types of yield. While that seems like a lot to cover, you'll find that it all hangs together as a means to answer the single question we have in this step. Where are we starting from in our improvement effort? So if you click on Next, we'll get started. Don't plan a journey unless you know your starting point. In Step 4, we will determine our starting point from which we will set our goals. Our primary measure for determining this value is the sigma level. The sigma level is calculated through statistical analysis of the collected data. Statistics is about organizing data, presenting it in a variety of formats, and drawing meaningful quantitative conclusions from it. We have collected the data and will now use a variety of statistical tools to draw conclusions. Click Next to continue. Variation is the enemy. You will often hear that phrase in connection with Six Sigma activities. What does this mean? Variation is deviance from the expected norm. The more variation in a process or product, the less predictable the outcome. So how do we measure variation? Range, the width of the distribution, and the standard deviation all indicate the level of variability in a process. Higher variance numbers, a larger standard deviation, or a broader distribution all indicate high degrees of variation in the process. Let's look at some simple data and see how the standard deviation is related to variation. To show you how variance and the standard deviation are calculated, let's look at a simple problem. You need to choose a route to work. You want to eat breakfast with your family, since you often stay late at work. From your normal departure time, you can take up to 35 minutes to get to work. You have a choice of two routes. The first route takes an average 25.3 minutes, while the second route takes an average of 20.6 minutes. Which route should you choose? You may be right or you may be wrong. The fact of the matter is you do not know the variation involved in this trip data to make an objective choice. For example, a longer route with a small variation may actually increase your chance to arrive at work consistently on time. We obtained 100 days worth of trip time data for each route. Each route's data was then loaded into Minitab as shown here. Now we're going to look at the data visually by generating a histogram with a best fit normal curve overlay for each route. We start by selecting the Stat menu from within Minitab. Then choose Basic Statistics, and then Display Descriptive Statistics. Before selecting the route, we need to determine exactly which graph to display. Click on the Graphs button to see your choices. You have a number of possible selections here, but we're going to select a histogram with a normal curve and click on OK. Don't forget, you can click on the underlined words to see their glossary entries. Click Next to continue. The only thing left to choose is which route to graph. Let's start with Route 1 and see what it looks like. You click in the Variables box and then click on which route you want to graph. Once you click on a set of data like Route 1, the Select button will become active. Click on Select and your choice will appear in the Variables box. After clicking on Select, click on OK. This is the chart for Route 1. It shows a strong cluster of times between 20 and 30 minutes, and only one trip exceeds the 35-minute upper limit defined by the vertical red line. Another way to look at it is that only one trip out of 100 would be considered a defect in your commuting process. So what happens if you do the same analysis on Route 2? Click Next to see the results. In the chart for Route 2, we can see that 10 of the trips are over the 35-minute mark. In the chart for Route 2, we can see that 10 of the trips are over the 35-minute mark. So if you take this route, you will be late 10 times as often, even though the trip is on average shorter. The standard deviation is also much higher at 7.4. Also, the normal curve is more flattened or broader than the one for Route 1. The standard deviation is a way of expressing variation in a set of data. The more variation, the higher the standard deviation, and the less predictable the process measured. Let's summarize the significance of the standard deviation. If your data follows a normal distribution, approximately 68% of all values will lie within one standard deviation of the mean. So a lowered standard deviation implies less variation in a process and its outputs, more predictability in the process, which implies better control of the process. Let's see how it works. We start with a simple histogram with a normal curve overlaid. First, draw a vertical line from the x-axis to the curve at the mean. Then draw two vertical lines from the axis to the curve. One is at one standard deviation lower than the mean, and the other is one standard deviation higher. 68% of all the data falls between the two lines. In other words, in this case, if Route 1 is chosen for future use, we can predict that 68% of the time, one would arrive in the office within 21 and 29.6 minutes after leaving the house. For additional information on variation and the standard deviation, click on Tell Me More.